Yeah, maybe it comes. Now let's try as a test the advection equation. We had the FTCS scheme here, and we found a little bit ad hoc geometrically that this Courant number C, which then equals A0 delta T by delta X, has to be smaller or equal 1. That was sort of the demand that we found last lecture. So let's try it. Here I have set up a case, 100 points in the x direction, an initial disturbance, and I specify a time step. A0 is 1, and here I said my dx equals to be 1. So in this case, if I try to run it, I will have something like this. So this is my x-axis, time level, we are at time level 0. And the red box here, that is my initial disturbance. I have 100 points in the x direction, so to describe it, of course, we have a little discrepancies here, but not much. So this is my initial state, and now we sort of let go in time. What's going to happen? The advection equation, he'll actually represent a transport of this signal that we have with the transport velocity A0, which is constant. So this correct solution, this square, is actually just going to move with the constant velocity. My choice of time step was so small that my CFL number here is 0.1. The demand was 1. So now let's see what happens. Thank you very much. It doesn't look good, does it? So clearly unstable. Clearly unstable. So if we try smaller time step, 0.01, it doesn't help. No matter what you do, this is unstable. So here, clearly something is dead wrong. If you, in desperation, try to go the other way, let's make delta t bigger. Now I have a CFL equals 1. I'm just on the safe limit. Wow. Definitely not stable. Definitely not good. So this no, we have no hope. And of course, if you go above, even worse. Yeah. Something is very, very wrong. Use the max-min method for this one. Take the sum of all coefficients. Well, here you have uj, he has a coefficient 1. uj plus 1, he has the coefficient Courant number half. And j minus 1, he has the coefficient minus c half, equals 1. Okay, we could use the method. Sum of coefficient is 1. Next, the demand, all coefficients positive. No, that's not possible. First one is okay, second one is okay, the last one is going to be negative no matter what you do. It's impossible. So here, we does not obtain any stability criteria, which is actually correct. This scheme is unconditionally unstable, no matter what you do. You have been given the Fourier analysis of this one, the von Neumann stability analysis, and it turns out yes, it is indeed unconditionally unstable. I can show you. The advection equation that we have here and our FTCS scheme, which then should have this Courant-Friedrich-Levy condition, finding the new one based on these three old ones. But here, the von Neumann analysis, inserting the arrow, do some calculations, you find the amplification factor is 1 plus something, which is definitely going to be bigger than 1. No way, this is going to be big trouble, big problems. So, what to do? What to do? We have to do something. So the first remedy, we don't use central space anymore. We try, say, a forward time, and then we use a backward scheme. Backward scheme. So call it also upwind scheme, first order upwind scheme, donor cells. You have several names for this one, donor cell, others as well. What should the philosophy be now? Well, geometrically we have this situation, space and time, my point J, and here we had a couple of neighbors. This was time level n, and now I want to go all the way up to time level n plus 1 for the new unknown up here. For the recipe here, we chose a spatial derivative involving these 2 points, and that didn't work. So what we are doing now is the following. We first assume this velocity a0 is a positive one. That means the information is traveling now to the right with this velocity. Then we say this derivative should not be constructed by using downstream or downwind information. The information is traveling to the right, so it should be quite okay to write a first order derivative at this point, since the information is traveling to the right anyway. So we rewrite the discretization scheme here by using a first order upwind scheme. So what will now the recipe be? uj n plus 1 minus uj n divided by delta t, as before, no change there, equals, no, not equals, sorry, that's wrong, should be plus, and then equals 0. So we have plus a0, and then I create a first order derivative using the upwind direction. So this will now read ujn minus uj minus 1 divided by one single delta x equals to 0. So I don't use the j+1 point anymore. I use j and j-1. So this is now my discretization star, only these 3 points. You pay a price for this. Actually, you pay several prices. This is now of order delta t, first order in time, but also only first order accurate in space. So it was much better to use central schemes, but it was unstable, so now we try something else. What will my stencil be if I want to write it in a programming form? Well, you have the new n+1 unknown equal to the rest. Throw everything else on the other side. What will it be? You can again construct the Cura number, the C, in the same way. We're going to need that one as well, delta t a0 over delta x. And then here you now have the coefficients for uj. What will he be? He will have a 1. And then he will have this one on the other side, minus the Cura number. And for the other one, j-1, time level n, this one is negative, but on the other side he will be positive, so he will have the coefficient, just the Cura number directly. So this will be my stencil. And now check the max-min method, sum of all the coefficients equals, well, uj has the coefficient 1 minus c, 1 minus c, and uj-1 has the coefficient plus c, so it's 1. Yes, you can use the method. And now the demand, all coefficients should be positive. Then we get the demand, actually the CFL criteria. Because the C itself, yeah, he's positive, of course. Now I've chosen A0 positive, so no problem there. But this coefficient also has to be positive. So C must be smaller or equal to 1. So we get actually the CFL condition now. That's the one that we found from the FTCS scheme, but here we didn't do any analysis. We just took it ad hoc, thinking in terms of information shouldn't travel longer than 1 delta x during one time step. But now we actually get the CFL condition based on a stability analysis. And you get the same criteria if you are using von Neumann methods. Let me show you. So here you have the upstream version. So the analysis now show indeed you get the CFL condition back. What about the numerics? Let's try to go back to the program. Go back to delta t 0.1. And then I choose the scheme, which then is first order upwind scheme, and then see what happens. Here we had the problem. CFL 0.1, so we should be well within the stability range. And yes, it is stable, but you see the price you pay. The correct solution is the red square box. He should not be distorted. This sharp gradient should not be smeared out like this. This is not good. This is not good. It's stable, as it should be, but very bad indeed. We can try to get it more accurate by choosing a smaller time step, of course. That should be the first obvious choice. But you see, it really doesn't help. You get the same solution, get the same effect. You take this, you get these sharp gradients that they are smeared out in space, which is not correct at all. So no, it doesn't look too promising. Stable, that's true, but very, very bad indeed. Now, just to show you, if you again go the other way in desperation, tries a bigger time step. Now the CFL is 1. You're just on the stability limit. Why? What happened? What do you know? Perfect. Now we have a solution. Correct. That's true. This is a correct solution. Why? Well, here I just say this is actually a coincidence. Look at your stencil here. Choose C equals 1, identical. This one disappears. And you say uj n plus 1 equals uj minus 1n. That means you take the value you have here and you just move it up here, which is of course the correct solution. But what you've done here then is actually using or solving this, the problem using hyperbolic techniques. You take your partial differential equation and you rewrite it in the direction of your characteristic curves. Then you will reduce a partial differential equation to an ordinary differential equation, and then you solve it along the characteristics. That's actually what you're doing. So you just here assure that your delta t hit the characteristic curve precisely, then it's okay. If this one is below, it will be stable, but very, very wrong. So here, this really doesn't help us, because in the end, in the full Navier-Stokes, we're going to have several terms on the other side anyway. Pressure, gravity, viscosity. So we can't really base our solution on hyperbolic ideas. So this really doesn't help. So here we just have to look upon it as a sort of a curiosity. So we are left actually now with an upwind solution. And in truth, first order upwind scheme, they are unconditionally stable, yes, but they should never ever be used. They are terrible, awful. Never use them, unless you have to. Sometimes you have to. You could use them to find sort of a quick and dirty solution. You can find them to obtain maybe a better starting point from your more advanced calculations, but they should never ever be used for any conclusive results. No way. They are terrible. Also, only first order accurate. So no, they are not good. We're coming back to this later. What we actually have done using this upwind scheme, you take your original partial differential equation and then you add actually viscosity. That was a bad viscosity. You add kinematic viscosity and then double derivative. That's actually the effect that you're doing. Remember, what is a diffusion mechanism? Diffusion, meaning, say, the viscous term in the Navier-Stokes, if you have any sudden jump in velocity, pressure, whatever, a diffusion mechanism, he will smear it out as time goes by. So he will sort of damp down any strong jumps. Of course, it's stable, stabilizes everything. If you are unfortunate with the value of the viscosity here in front of the double derivatives. If that one goes negative viscosity, that's not any physical property, of course. But what would happen if you had negative viscosity and you had a sudden jump? The opposite will happen. Then you will have a solution that's increasing any jumps. Of course, he will be very unstable and explode. We are going to address this then more tomorrow about numerics and the viscosity, and then the total viscosity, which actually may become negative and then destroy everything. Yeah, any questions so far? That's okay. Instead of choosing this first order upwind scheme, which then is here stable, but at a nasty price, we could have chosen something else. There is a rumor saying that if you switch the first term there, the time derivative scheme, instead of a forward time, you use a backward time. There's a rumor saying that that one is unconditionally stable. So if we now do it again, but now I'm using a backward time central space scheme. That means a full implicit scheme. Full implicit, so you do now the following. Full implicit, the time derivative as before, point j n plus 1 minus the old one over delta t. So he's still first order accurate in time. And then I write plus a 0, and then I want a central space derivative. So it's uj plus 1 minus uj minus 1 over 2 delta x. But these are now taken at the new time level. N plus 1. N plus 1. And then equal to 0. What's the accuracy here? Well, it's actually the same as before. First order in time, second order in space. So now, in time and space, we have it somewhat different. J plus 1, no, this was minus 1, and here j plus 1. Time level n, time level up here, n plus 1. So we use this point to find the new one up here. But you see I have 3 unknowns up here. So actually I have my discretization star is sort of turned upside down. This will be the fully implicit scheme. And to solve it, well, if you throw all your unknowns on one side, what do you get? Well, here you will get something like this. Let's see, you will have uj n plus 1, this one. But these are also unknowns. So they will now read something like plus, say, multiply with delta t. You will have Courant number half of these two guys, uj n plus 1, uj n minus 1. And then what do you get on the other side? Actually only the old one equals ujn. This will be your programming task. Solve this equation system. Of course, it's fully implicit, meaning you have to solve an equation system. You have 3 unknowns here, so you have to solve everything at once. For a one-dimensional problem, that's quite trivial. For 2 and 3D, that can be a pretty tough numerical task. A lot of calculations involved using fully implicit schemes. What's nice about it is that, according to theory, numerical theory, it should be unconditionally stable. Here you see we can't use the max-mean method anymore. So doing the stability analysis here is more tricky. You can do it with von Neumann, with the other methods, but I won't go into the details there for you. You can have a peek for yourself if you're interested. But let's just try to see the effect of this fully implicit scheme. So I go back to a smaller time step, 0.1, and then I choose fully implicit scheme, number 5. To solve it, my choice number 5 here, I just used the backslash in MATLAB. I have a coefficient matrix, and I have the right-hand side vector. That's just the old use. So there you can very easily solve it with two sentences. I tried even with an iteration scheme. That also works if you want, but then you have to do many iterations. So I used a direct solver, the backslash in MATLAB. Very easy. The A matrix set up somewhere here, I think, yeah. And the B as well. So let's just try to run it. CFL is 0.1, and now we have a fully implicit scheme. It's central space. Well, should we call it stable? I'm not so sure. It doesn't explode, but you have a lot of noise. But it's still actually stable. It is, yes. So again, you can try smaller and smaller time step to see if that helps for the accuracy. But actually, no, that's not any good remedy. You still have noise from any gradient, but it will not explode. It should be stable no matter what. But again, very bad solution. Very bad solution. So no, it's not a good approximation at all. You can go the other way here also. Delta t equals 1. Now we are on the stability limit for that was for the upwind scheme. Here it should be stable no matter what. And actually it is. And now I can even go to higher delta t's if I wanted to. Say 1.5. Now see what happens. Yes, still stable. Still very bad though, but you get a solution, and yes, it is unconditionally stable, but not a good solution. People have been fighting this equation a lot, trying to find a good discrete scheme for it, and they have a lot of problems with it. I tried a couple of here. You have a hybrid scheme. You take 50% of the upwind and 50% of the central scheme, just to see if that helps, and helps a little bit, but still not good. You can try a lot of different schemes here. Lax-Vendroff scheme wasn't that nice either. So very hard to find a correct solution for this very simple advection equation. The fully implicit scheme, yes, it works. and it's stable, but it's not accurate anymore. If we now try looking at the other problem that we had, that was the diffusion equation. Let's see now. The diffusion equation. I'll just show you the philosophy here. Mute. The diffusion equation, it read time derivative equals double derivative in space. When we had written it in the non-dimensional form, choosing the proper timescale, the viscous timescale, we had this equation. And we had uj n plus 1 minus ujn over delta t equals double derivative. J plus 1, 2 times center point, plus uj minus 1 n by delta x square. That was the recipe, and this one we rewrote n plus 1 equals, and what did we get here? We had ujn here, multiplied with 1 minus 2 times r, we called it, plus r, and then uj plus 1 plus uj minus 1. And the stability analysis showed then that the r, it had to be smaller than 1/2 when we used the max-min method. Here, one coefficient is 1 minus 2r, and here we have two coefficients, both r for these two guys. Sum of coefficient is 1. You could use the method. Criteria, r has to be smaller than 1/2. That's the demand. Now look at the startup of a cuvette flow. Here you have a solid wall. Here you have the top wall. All of a sudden starts to move. What do you get? You start with 0 velocity. The analytical solution should be a straight line, and in between you will have velocity profiles looking something like this, and as time goes by then he should tend towards the straight line. Of course he should. Let's see if that is the case.